Yeah, I kept the whole garage door.
Okay, guys, this might be a review for some of y'all. So what is an electrical circuit? Path for current flow. Oh, it went backwards. What's an electrical conductor? From the source to the load. So, what's an electrical insulator? That sounds pretty good. What natural metal is the best conductor of electricity? What are the two most often used electrical conductors? What is voltage, current, resistance, and power? Go ahead, DC, you should know that. What's the basic difference between DC and AC? Look at that a little. Somebody else said DC. What? Huh? Yeah, but why do we want something to offer? What is the cycle frequency in hertz? Anybody know what that is? We're going to go through this, by the way. Y'all don't have to know these. We're just seeing what y'all know. What is an electrical open, electrical short? I know the difference between two. Books are down there?
Open
Path,
breaks the path.
like what's a short?
The short is path that reaches resistance.
Okay, we'll look at that. What is required for a basic circuit, guys? Gotta have a sword, path, and a load, right? What's the difference between series parallel circuits? Everybody's had DC in here, right? Everybody had DC? So what's the same in a series circuit? Current. So current's the same through each circuit unless something changes in the circuit. This happens even on, y'all probably saw that test on DC where they said, I changed this resistor, and people say, well, nothing changes because current is the same in a series circuit. It's not the same if you change something in the circuit, right? You understand that? It'll be the same in that circuit, but it varies depending on the co-op. Parallel?
Voltage is the same.
Yeah, the voltage is the same in all your loads inside the circuit. And series parallel. Combination of two. Series parallel will run into electronics a lot. There's something, we have these devices we call solid state devices. Transistors, SCRs, triacs. These guys have to be biased to turn them on, to make them operate. So you have to put precise dosages on. And we do that with resistors, series parallel circuits. So if you're in, if you take solid state, if you're in the AUT degree, you won't take that. If you're in the ILT degree, you will take it. You'll learn how we use these resistors, these series parallel circuits to bias these solid state devices. What is the difference between resistance and reactance?
Resistance is the opposition, and reactance is when a variable changes and.
We'll see. Like I said, we'll learn. So resistance, we'll find the difference in those. So this is a chart of conductance. So y'all said copper is the best conductor of electricity, is silver. Silver is the best. Copper is a slow second, a very close second. Silver is the best. What's the problem with using silver? Very, very expensive, and it's very flexible, right? I understand that. Silver oxide is pretty neat. Silver oxide is just silver rust is just as conductive as silver. So we don't use a lot. We do use silver, but we use silver as a plating. You know, y'all see these commercials about these people selling these coins, and they say 0.1 million, 1,000 gram of solid gold, right? You understand? And what it is, it's made out of some metal that can be plated, and they put a thin plate of gold on it. And if you get them and rub them a few times, what happens? It fades, yeah. People buy the things, right? But you need to watch those commercials. So silver, we use that as a plating, especially on what we call contacts. Contacts is a method that we use to make and break circuits. So basically, if you was to look inside a light switch, you see it's just got two things, and they just touch together. When they touch together, it makes the circuit and allows current to flow, and then you flip the switch in the other direction, it does what? Well, right there where those two wires are come together, we need to have that's a potential for a higher resistance, right? You understand? And anytime I put current through resistance, what happens? We get what we call a voltage drop. And also we get I square R, which is heat. And we don't want our switches to get hot. So this is why switches don't get hot, because they have no R, right? You understand that? So what we do is, if you ever look them, you'll look at the contacts, and they'll look silver because they put a little silver plating there on the end of the copper, just where the wire touches. Then copper. So copper is a really, really good conductor when we get into lower voltages. So copper, the problem we do have with copper is that copper oxide or copper rust is an insulator. So we got to coat this stuff. We got to take care of it right. If we just leave it out in the air, eventually it's going to corrode them. This even happens sometimes in your wall outlets. They'll have a wall outlet that's been going on for a long time, and all of a sudden wall outlets, guys, are not supposed to get hot, right? You understand? If it gets hot, what does that mean? It means there's an R in there, right? That's not supposed to that's not supposed to be there. So to get heat, we've got to have an R. Now you probably learned two formulas. You run several formulas for power. What was the formulas y'all learned for power? Yeah, no. V is equal I, right? I'm sorry. P is equal to V times I. And then we got P is equal to I squared R. And we got P is equal to V squared R. Which is basically taking this formula right here and then transposing what Ohm's law says V is equal to. Right? And then transposing it and seeing what I is equal to. And that's where you get the I squared R. So if I've got R, I've got current, and to get power, you've got to have a resistance, right? Everybody understand that? And it varies with the square. So if you've got an outlet that's getting hot, or if you've got a wall switch that's getting hot, how much resistance should a wall switch have? 0. You don't want it to produce power, right? You want it to control your circuit, but you don't want it to do electrical work. So if you've got a wall switch that's getting hot, what should you do? You should change it. Yeah, because metals, when they get hot, they oxidize faster. So you get hot, then your copper starts oxidizing. You add more R. You're trying to pull current through that thing. It gets hotter, and eventually, guys, you can get what we call a fire, right? Followed by gold. Most people want to say gold. I'm glad y'all didn't say that. So most people, especially first people, you talk about that, they say gold is the best conductor. Gold is not. Gold is actually the third best conductor of electricity of the known metals. And I don't know if there's any unknown metals out there now, because we've been here quite a while looking for metals, right? They might find some if we ever make it to Mars. But right now, but gold, what advantage does gold have over copper? Not much stronger. I mean, they've found ships, and salt is very corrosive, right? You understand that? That's why if you live up north, most of the time they undercoat all the cars and everything with a rubber type stuff, because that salt gets up on the car, because they use a lot of salt, then it'll just rush the whole bottom of the car. So the problem with salt is that it's very corrosive. Salt water is very corrosive. They pull gold up out of the ocean that's been down there for centuries, and they break that stuff off, and it's still what? It's gold. So as far as we know, gold does not oxidize. It doesn't oxidize in our, so anything that we're going to expose to our atmosphere that has a lot of corrosives in it, we use a lot of gold plating. So a lot of things you'll go out and buy you might buy an HDMI cable for your TV and they say gold plated. And it's gold plated. It's not gold, it's gold plated. So it's got copper conductors because they're better, but right at the very end where they make the connection, they put a little thin gold plating. And you pay a lot of money for those cables. All you gotta do is just take the ones out and push them in a little bit. Go ahead.
That's why they use gold instead of silver inside the computer.
Yeah, they use a lot of gold, and a lot of your computers are getting away from gold because they figured out that by the time gold corrodes, you've got rid of the computer anyway. So tin oxidizes. It gets along with copper real well too. So, but it oxidizes at a lot slower rate. So most of your computer and stuff now use a lot of tin in there because it's a lot cheaper. And by the time it starts oxidizing, you're ready to do what? Get a new one anyway, yeah. So. And then we fall down through the other end. Aluminum. Aluminum is actually the fourth conductor of electricity, fourth best conductor of electricity. But we use this guy. Alabama Power, our power companies use this a lot. And what advantage does aluminum have over copper?
It don't get hot. You don't get it hot.
Well, no. Aluminum would actually get hot. Aluminum would get hotter for the same current.
But it don't.
Cheaper and it's lighter. That's the big advantage. It's cheaper and it's lighter. So here they're trying to run all these power cables hundreds of miles, and these towers have to support that metal, right? You understand? So if they use aluminum for one thing, it makes it lighter, so their towers that they're running this high voltage on don't have to be as strong, and plus it's a lot cheaper. But it oxidizes and it has a big coefficient of expansion, which means it changes. So this guy is real hard to splice. We got to do some really good splicing on it. You know what splicing is? What's splicing? What's splicing? Well, the problem is that think about how far we get our electricity from the Tennessee Valley. Bessemer is on TVA. We're not on Alabama Power. So all our electricity comes from up in the Tennessee Valley. And they've got to run that down here on wires. How many miles would that be? A couple hundred miles. You think they have a wire that's a couple of 100 miles long? So what do? They put it on these big spools, and sooner or later it's going to come to an end. And then they're going to bring another one up, and they're going to hook them together somehow. The act of hooking conductors together, we refer to that as splicing. So you're out there and a tree falls across a power line and it breaks it. Do they run a new line? Probably not. What do? They just come up there and splice it back in together. So it allows us to join conductors together. And termination, what's termination? Termination, eventually all conductors, what does conductors do? Conductors have one fixture in life. What's their function in life? To carry the current between the source and the load. That is the function of the conductor, is to carry the current between the what. So sooner or later, all conductors come to an end. And so we have to have the ability to bring the conductors to an end, and we call that termination. So this is where you do your splicing. This is where you put your butt splices on, where you put your terminals on, and all that kind of stuff. That would be called termination. And we teach a class called EET 226 is called cable splicing and termination. So we'll teach that class. 4 weeks we do copper, and then the other 4 weeks we do fiber. So copper has a lot more resistance, and I square R, so that means aluminum would get hotter for the same length. It would have more resistance for the same length. What determines the resistance of a conductor? And this is definitely on the next slide, but let's see if we can guess. The resistance of a conductor. Everything has resistance. We don't have anything that has zero resistance. We do have superconductors, but we don't deal with that. Superconductors have to be ran in liquid nitrogen. They have to freeze them. So, Huh?
Material
The
size.
size, yeah, the material. Good. The size. What'd you say here? Length. And 4. Somebody said this. Temperature. So metals, when you heat them, their resistance goes up. When they cool down, and this is why supercomputers are frozen, right? Because they want the temperature to be as low as they possibly can. They don't use these, by the way, they use alloy to try to get the resistance level. So every wire has resistance, unfortunately. Aluminum has more resistance than copper. And anytime we have resistance, and we put current through a resistance, what do we get? We get what we call a voltage drop. So line crews call this line loss. They say they have so much line loss, which means they lose voltage over this. So this is the periodic table. And of course, you all see where the conductors fall into. There's copper, there's silver, there's gold. And here's where aluminum over here. Inside the blue, called a core metal. So copper is almost a. So what determines if it's a conductor? Anybody know? No, should have had that in DC. Or the valence. Yeah. So anything that has 1 to 3, we say these are what? Conductors. And anything that has 4, we call these what? Good. And then anything that has between 5 and 8, we call these insulators. And besides for all, so the valence shell could have anywhere between 1 up to 8. So that would be the last shell out there. So aluminum has 3. So that's what this number is right here. It shows you the valence electrons. And that's, y'all can't see it. So aluminum is right here. It has 3. So it's right on the verge of being a what? An insulator, right? And then of course your copper has 1, gold has 1, and then I'm sorry, silver has 1 and gold has 1. I can't see that. So aluminum is up here. It's almost a semiconductor, so it has quite a bit of resistance. Why do we use it? We'll talk about that in a minute. Silver commonly used as plating. Copper is extremely good. Gold is very good. Commonly used as a what? Plating. Gold. Aluminum is good. It's commonly used for high voltage electric conductors. And copper and aluminum are the most often used for electrical conductors. So what is our power company selling us? And what's power equal to? So technically, guys, if the power grid was 100% efficient, if I turn on a 100-watt light bulb at my house, my power company would give me how many watts? 100 watts. You understand that? So when we go through transformers do not change power. If the transformer was 100% work in equals work out, we cannot increase the amount of work, right? You understand that? So it means if I need 100 watts out, the transformer is going to give me 100 watts through it. So transformers don't change watts. What does transformers change? They change voltage. And they also change current. We'll have to look at that. But most people say they change current. So if power is equal to V times I, then I, the amount of voltage drop we get through an R, right? V is equal to I times R. So it means if I can lower the current, I will get a lower voltage drop, right? Y'all understand that? So I is equal to P over V. So what are we trying to sell you? power. So the higher the higher the voltage I can transmit that power at, the lower the current is going to be required to transmit that power. That makes sense? So that means if I was transmitting my power at 750,000 volts, I could send 750,000 watts of power with 1 amp of current. Now, what's the problem with 750,000 volts? Y'all ever see Eagle Eye? Y'all see the movie Eagle Eye? Y'all see that? What happens when that high voltage line fell down on that guy? He just evaporated. So high voltage is extremely dangerous, but we can, and where are your high voltage lines at? They're way up there, right? You understand that? Way away from ground. The closer we get to ground, which is what it's looking for, we have to start lowering the voltage down. But when we lower the voltage down, the current has to go up to provide that what? Power. That makes sense. So the advantage of, and this is one big advantage of AC, is that we can change the voltage going through nothing but water. We can step it up real high with step-up transformers for what? For transmission. And then when we start getting closer to you, what do we start doing? Stepping it down for safety. So you got 2 voltages in your house. What's the 2 voltages we run in our house? Yeah, 120 is what NEC says. They call that the nominal voltage, but it's plus or minus 10%. And then we run 240. All your high wattage loads runs off what? 240. Wow. What advantage does high voltage have over low voltage? Power's power. Power is equal to V times I. Right, to understand. So I could send 5,000 watts of power with 5 volts. I could, right? It would be hard to do. So what advantage does high voltage have over low voltage? The problem is, guys, is I've got to run that 1,800 watt heating element on my stove. Right? You understand? If I was to do that at 120 volts, the wire that I would run out there would probably be like 4-gauge wire, and it would probably be about that big. Right? You understand?
And anything less would melt.
Anything less would melt. So the only real advantage of high voltage is it takes a smaller conductor to provide that power. So all your high wattage devices are run off 240. So they can run smaller conductors. So instead of running them through your ceiling, they can run them through your walls. Right? You understand? So 240 is cheaper to install. It's not cheaper to run. Power's power. You don't pay for voltage. You don't pay a current bill. You don't pay a voltage bill. You pay a what? Power bill. It's just that the lower the voltage I deliver that power, the higher the current has to be to deliver that power. I've got to run that through conductors. Conductors has resistance. What determines the resistance of a conductor? The size. So I could go to, so Alabama Power is trying to send me 750,000 watts, and they're doing it at 120 volts. What size would the conductors be? That'd be as big as buses, right? You understand that? Just to get that there. So they send it at 200,000 or 300,000 volts. Now they can use, instead of using copper, they can use what? Aluminum. Right? And they can use a smaller gauge wire. So that's the purpose. That's the only advantage high voltage has over low voltage, is that we can run it with smaller gauge wires. Everybody understand that? So 240, all your high wattage devices are on 240. What's the big advantage of 240? It's twice as dangerous as 120. 120 is dangerous. 240 is really dangerous. Anybody know what's considered to be the lethal voltage? According to the 70E standard, 50 volts. So you're dealing with voltages that are considered to be lethal. Does that mean you can't be killed by 50 volts? Yes, it's just high. It's just unlikely that you can be killed. When you think above 50 ohms, what do y'all have to start doing? Y'all have to start putting on a special PPE, right? Force, any reaction that attempts to change the motion of an object. Work, the transfer of energy from one physical system to another, especially transfer of energy. And that's what people don't understand is basically if everything was 100% efficient, power in would be equal to power out. Everybody understand that? But it's not. So we'll never get as much power out than we get in. So basically, so work out is never equal to work in. So work out, it will always be a little less. So all your levers and stuff like that, you're not increasing work, right? Understand? So power is equal to force divided by distance. And of course, distance is inversely proportional to speed. So this is the formula we use. So when we calculate power, we use force times speed. And what's the force we use? What's our force? As attempting to cause something to change directions or move. What's our force in electricity? Starts with a V, volt. And then what's our speed? Current. That's the current. That's what we're doing when we calculate power. We use amperes. Amperes is the rate of speed. Anybody know what 1 ampere is equal to? Did y'all learn that in DC? Was it like 6.28 times 10 to the 18th electrons moving past the point in 1 second? I always wondered who counted those things. It was calculated, yeah. It's pretty. So 1 amp, we use 1 amp, which basically is a representation of speed. Everybody okay? This is stuff review, right? Basic stuff, right? All electrical devices operate from electrical current, but we can't have current unless we have voltage. No, we can't have power without current, but we can't have power without voltage either, right? You understand? Because power is the rate of doing work, right? So we got to have a force and we got to have a speed. The amount of power produced by these devices is determined by the amount of current that flows through them and the force that is causing the current. This is our power. Back in getting to physics, we say work is equal to force times distance. How much work you do. The power is the amount of current is controlled by the amount of force divided by the amount of opposition to the flow, right? Everybody okay? This is a review. Everybody okay? I've had this before, right? Please? Yes? Electrical current consists of atoms of electrons that have been forced to move by different electrical potential. And that it's called an EMF, so you need to get used to that. Basically, we teach voltage, but you're going to run into a lot of books that teach voltage as E, which stands for electromotive force. Those are both legal. So you'll see people don't get confused when you get into a book and it says E was equal to I times R. And the problem we have is that we have V on both sides of the equation. So you say V is equal to I times R, right? You understand? And you say, okay, V is equal to 10 volts. So you got V on both sides of the equation. A lot of mathematicians don't like it on both sides of the equation. So that's why a lot of books use this electromotive force. So you'll see E. So E or V is legal in all these formulas. The strength of the difference in electrical potential and the amount of opposition to the flow of current determines at what speed the electrons move. Everybody okay there? This should be basically a review, right? Yeah. Some materials such as metals allow electrons to move freely while others such as rubber do not. For this reason, most metals make good electrical conductors while materials such as rubber, Teflon, stuff like that, they make insulators. What do we need insulators for? This is another slide, but what do we need insulators for? Yeah, to keep you from getting electrocuted, right? It allows us to handle conductors, right? Understand? And plus, it allows us to bring conductors in close proximity to each other, right? We have to have insulators if I'm gonna run a cable. So what is a cable? Well, a cable is a group of if 2 or more conductors that shares a common jacket. Well, if we're gonna put 2 or more conductors inside there, every one of them's gonna have to be what? Insulated. So it allows us to handle that stuff. The problem is when we put insulation on, so what do we wear in the wintertime to keep warm? We put insulators around a conductor, what's that going to generate? Heat. What happens when we heat a conductor? Its resistance goes up. So this is when we look at some of the ampacity, the current carrying capabilities of a conductor. NEC has changed the current carrying capabilities depending on what insulator you use. So if you're ever in the house wiring, you can't say a 14 gauge wire will handle 30 amps. That's 30 amps if it's uninsulated, right? You understand? So we'll show you all that table too. EMF or voltage is the difference of difference of electrical potential that forces the electrons to move, but they only move if you have a path, right? Everybody okay? Yes?
Where is
It's under course content, under lecture slides, under introduction.
That's the only one I didn't know.
Introduction. Okay. I think that's a good question. Current is the flow of electrons that results from a difference in electrical potential plus a path, right? Resistance and reactance. So this is a little definition. Resistance and reactance are the opposition of flow. Resistance does not vary with frequency, and reactance varies with frequency. We're not going to talk much about reactance. People that tell you that AC and DC are the same, they have no idea. We had a guy that interviewed for a teaching job here. And he decided to do his sample lecture on transformers. And you know what he said? He says, transformers increase the power. Transformers don't increase power. Power in equals what? Power out. Guess who didn't get the job? Transformers don't change power. Power in equals power. Like I said, if transformers increased power, Alabama Power would use that they'd use them to generate power, right? They'd have a little motor out there, a little car out there running a little tiny alternator, and they'd use what? They'd use transformers to give you that power. They wouldn't have that big old power plant down in Wilsonville, right? You understand? That's got generators the size of a house, right? So transformers don't change power. In fact, your car radio, you think you get a power gain, but all that power is coming from a power supply, right? You understand that? Yeah, go out there and disconnect your battery and turn your radio on. And see if that volume control works then.
Might work though because I'm
No. Oh, with the alternator running, yeah. Because now you're getting your power from the alternator. So AC gives us something called reactance, and reactance is very, very important. We use these for filters, electrical filters. You know what filters are for? Get rid of stuff. So, well, not ground, like it gives us the ability to tune in a radio station. So I get out in my car, I tune in a radio station, and filters block everybody else. Right? Understand? So without filters, we wouldn't have TVs, we wouldn't have radios, we wouldn't have anything. Plus noise that gets into your system. So you got your spark plugs out there firing, generating noise all over the place. So what we'd like to do is not let your radio pick that up anymore. So the radios do what? They filter it out. Also, they create what we call phase shifts, which allows single phase motors to rotate. You literally got to deliberately shift something. And I'll try to show you that too. These are reactance devices. Electrical circuit is a complete path for current flow. Basic electrical circuit consists of a voltage source conductor, and a return conductor and a relay. The problem with AC though is your source conductor and the return conductor are constantly what? They're swapping. DC, they don't change. Most electrical circuits also consist of at least one electrical control device. So like here, I got these lights right here off, I got those lights on, we got some control device that allows me to do what? Yeah, to turn them off and on. Human body, if you understand that, so human body, what do we have that generates the difference of potential? Heart, yeah, the heart generates the difference of potential, right? Which causes what flow? Blood, right? Blood goes through vessels, right? We have veins and we have arteries. Those are similar to the what? So your heart is similar to your voltage source, right? Your vessels are similar to the conductors. And your muscles are similar to your what? To your legs. If you understand that, then that's basically what we do. Right? Except we don't want, if we open up a blood vessel, we got problems. Right? We deliberately open the electrical circuits, right? Circuit works similar to the human circulatory system. The heart creates a difference of pressure. So we don't, and a lot of people think voltage moves through a circuit. Voltage don't move through a circuit, but we can get what we call a pressure loss. Anytime we go through a resistor, then we're going to lose pressure going through that thing, right? We call that a voltage drop. Or a blood clot, yeah. Here we call it a blood clot. Well, we do have resistance in our body. And of course, one of the first things they do when you walk into a doctor's office is do what? Check your blood pressure, checking it. So we use a voltmeter, right, to check our pressure. So we already talked about this. So the voltage source is similar to the heart. The vessels are similar to the what? Conductors, and then the muscles are similar to the voltage. And all the blood that goes out should do what? Come back, right? So this is the basic circuit. Animation. We teach what we call electron flow. Originally, when they came out with electricity, and they decided to name the polarities of a DC source plus and minus, they considered the plus to be the highest potential. So originally, when they came out with electricity, they thought it flowed, the current flowed from positive to negative. So when they came out with solid state, they still was using that. We call that conventional current flow, and they were still using that. So just about all our solid state symbols use an arrow, and the current flows against the arrow, which is, you have to get used to that. But after a while, they realized that what was flowing in the circuit, the electrons. So we call it conventional current, and we call it electron flow. Guys, some books teach conventional current. There's still a lot of engineering classes that teach that, but it doesn't change anything. It doesn't change any formula. The only thing it changes is your rule for magnetism. When you create an electromagnet, trying to determine which is the north and which is the south. So one of them is like the right-hand rule, and for conventional current, it might be the right-hand rule. For electron flow, it might be the what? The left-hand rule. So that's the only thing I know it makes any difference. It don't change any polarities. It's not going to have any to how you hook up your meter. It don't change any math formulas. All it does is change your rules for magnetism, electromagnetism. Voltage source, we call this the source conductor, the load, and then the return conductor. Are we okay? Of course, y'all seen these. So y'all work the rest of these. Did y'all enjoy these? That's one, yeah. You have to start on the outside and work back toward the front. Parallel is pretty easy. What we found out is a lot of people, once they learn series, they try to apply it to everything. What's nice is that this class right here, guys, we have no series parallel circuit. In motor controls, there are no series parallel circuit. In fact, we have no multi-load series circuit. In motor controls and PLC, we either have one load series circuit, or we got multiple load parallel circuit. And you're not going to have to solve for I or E or P or anything like that. So not used in electrical controls, guys. So here's a series circuit. Everybody okay with that? Everybody knows that? One load feeds into the other. The voltage is divided in the source proportional to the load and proportional to the total opposition in the circuit. So what advantage do series circuits have? Well, series circuits allows us to use lower voltage loads that are rated at lower voltage because the voltage is divided out. The bigger problem we have with the series, so now I can have my Christmas tree lights and use these little old tiny lights, right? You understand? They're not rated at 120 volts. They're usually rated about 2 volts, right? You understand? Right? But if I can put, or maybe 4 volts, if I can put so many of them in series, right? You understand? They all have the same resistance, then you can hook them up to 120 volts and still not mess them up. The biggest disadvantage we have with the series circuit, of course, is that if we lose one load, with one load open, the whole circuit is going to go. That would be awful. Think about your house. You know, you have a light bulb blow out and your whole house goes up. We use it a lot in electronics, but you see series circuits all the time when you put up your Christmas lights. But they're not series anymore. Some of them still are. Now most of them are series parallel. So if you lose one bulb, you might lose 12 lights, but you still have the other strings, right? So your Christmas tree don't go totally dark. Since there's only one path, the current through each load is the same throughout the circuit. Everybody okay? So this is a series circuit. There are no multi-load series circuits used in relay logic, and there's single load circuits in relay. So there's no multi-load. We'll use single load circuits, right? And then we use parallel circuits. You're not going to do any calculations, but you need to understand the features of the series circuit. Everybody okay? And so this shows you the current flow, my animation. Parallel, the voltage to each load is the same. All loads are connected across the voltage source when all the control devices are true. So normally we have control devices. And that would be awful if you couldn't turn your lights off and on, right? As soon as you turn the power on, everything in your house came on. So normally a circuit has control, some type of control device out there that we can turn them on. So what advantages does a parallel circuit have over one of the major advantages of a parallel circuit as over series?
One dot is a load.
Yeah, you can add and remove loads and it has no effect on the other load. So we can turn lights off, we can turn them on, we can turn TVs on and off, we can unplug things, we can plug things in, right? You understand? So basically Alabama Power or the power company is parallel and your circuit is parallel, your house is wired in parallel. So we can add and remove loads without doing what? Without affecting any of those. So this parallel circuit. Series parallel, we see these, we usually don't run into these until we get into electronics. And this would be the way we bias solid state devices to determine how they operate, where they operate. There are no series parallel circuits in relay or PLC logic. What's logic, by the way? Logic is a method that we use to look at multiple signals. So we have what we call AND logic. AND would be this and this and this and this. We have what we call OR logic, which would be what? This or this or this or this, right? Huh? Then we have what we call NAND logic, which is opposite. We'll look at those. But it's called a programmable logic control. So what we do is we're going to look how we connect control devices to either do what? ANDs, ORs, NANds, NORs, and NOTs. Those are the 5 basic logic. And we'll learn about those this term. So when we use relays, that's what we do. It's called relay logic. And of course, what this has moved into is your programmable logic controller, right? PLCs. And that means that's what they do. They replace what we used to do with relays. Control devices control the flow and produce no electrical work. So to produce electrical work, you have to have an R, right? You understand that? So your control devices, you want to have 0 R. Trouble is when we get into solid state devices, there's no such thing as zero R, but they have a very, very low R. The connection of control devices does not determine if the circuit is series, parallel, series, parallel. Control devices, you can look them up in series, you can look them at parallel, you can look them up any way you want to. You can look at series, parallel, and that does not determine if the circuit is a parallel circuit or a series circuit. What determines that is how you connect the loads. So the loads in the circuit determines what category of circuit. Everybody okay? Of course, y'all familiar with some push buttons, right? So this is the control device. Y'all deal with control devices all the time. We can turn our stove to off, on or off. We can turn our lights on or off. We can turn our TVs on or off. We can start our car and stop our car, right? So we can turn the lights on our car off and on and off. So most of your circuits are going to have some control device in there that we're going to be able to turn things on or off. Everybody okay? Switches, push button, relay contact sensors. Systems are devices that convert a physical stimulus into an electrical equivalent. So automation, what is automation? Well, yeah, or little or no human intervention, right? Well, totally, we don't currently have very much total automation. And probably what's nice is that automation is done by computers, like PLCs. These guys break and these guys have to be programmed, and we still have people. So more and more of the jobs that we used to call labor jobs, these jobs are slowly being replaced by what? Automation. But these guys still have to be what? They're electromechanical devices guys. You know what that means? It means two things can fail, right? Your car is an electromechanical device. They can fail what? Two different ways. They can fail what? Electrically, or they can fail mechanically. And they don't fix themselves. So these guys, they don't fix themselves. They don't program themselves. They don't fix themselves. They don't maintain themselves. So usually mechanical devices have to be maintained, right? You understand? It's just like your car. What do you do? Hopefully you do it in your car. What do you do pretty often? Make sure you change the oil, right? Every 100,000 miles or so, you need to change your transmission fluid. And if you do that, odds are you'll get good life out of your car. It don't guarantee that you're not going to break. So these are some things that we use in controls. And you can see some of these up here on these panels up here. So this is an electrical control circuit up here. And that we look up there. And you can see the push buttons up there. So those are control devices, right? I don't know if we got any more circuits wired up in here. This probably works. So we have a bunch of push buttons. That switches, select switches, stuff like that. These are just devices that we use to control things. Then we have these guys. These are called limit switches. This would be an example of a sensor. Anybody ever seen these out? You ever see these in industry? What do we use these things for? These are switches, but they're not controlled by you. They're controlled by something hitting up against this operator. And then when the operator hits, it moves and either closes a contact or opens. These are electromechanical devices, but they're really, really rugged, and they can operate in very harsh environments. A lot of electronics don't like a real lot of harsh environments. So I guarantee you, if you're working in an automated system, you're going to see these guys. The biggest problem we have, of course, is they're electromechanical devices. Which means what? They can fail two different ways. They can fail what? Electrically. In fact, I think we got a limit switch over there. That's right. And this was opened up. You can actually see what we call contacts. They usually got a snap like that. They usually don't close real fast or slow. And they have a little, like a plateau operator in there. As soon as you go across that thing, they snap. But we want electrical circuits that make and break real fast, right? Because the slower they break, the odds are the longer they're going to create an arc, and they create an arc, it creates ozone. Ozone has low resistance. So normally if an arc is created, it's hard to get rid of, especially DC. AC helps to extinguish it because AC drops to zero. Alabama Power transmits 60 AC cycles per second, so that means it drops to zero 120 times a second. So AC has a tendency to self-extinguish. It don't mean it is, but you got enough push, right? But it has DC. Once you get an arc with DC, it's hard to extinguish. So we have to use techniques. We had a crane out at U.S. Steel, and all the cranes in this plant was radio operated. So they had a bunch of relays up there, and they had one where the guy that was designed, they call them blowout coils, was designed to extinguish the DC arc once it was created. And these are real high current things. It had fell off. So when they opened up this thing to turn off the motor never turned off. So it would go up and jam up the things and kick the overload. And we got up there and saw what was going on, and the thing was arcing. And we blew it out. We actually blew it out. And then we remounted the thing that did that. So DC is hard to extinguish. So that's why most of these things do what? They snap. In fact, your wall switches, some people call them snap switches, the one you turn your lights on and off. These are electronic sensors. So we'll look at some sensors when we go over to, we'll go over to the production line and actually see some PLCs that are actually operating, controlling an automated system. And the name, the automated system, depends on what we call sensors. So sensors are going to make sure things are in the right place at the right time. They're going to make sure they're the right orientation. They're going to make sure they're either metal or non-metal, or if they're this or that, and that's what sensors do for. Okay. And these are solid state sensors. These are electronic sensors. So we'll show you all those. We'll talk about the different ones. We have some that sense nothing but metal. But y'all run into these guys all the time. So how do those red lights out there know when you're up when you need to make them change? It's got a sensor out there, and what's it? It's a metal detector. That's all it is. It's a metal sensor. You can actually see that loop on the thing out there. That's it. Actual metal detector. That's all it is. When they do work, the one out here, the main gate's not working anymore. It changed. We have ones that sense metal. We have some that sense solid. We have some that use reflected light. We have one that use black light. We have sensors that use ultrasonics. We have all different types. We have temperature sensors. We have pressure sensors. We have all different types of sensors out there that sense what's coming on. And then what we'll do is the sensor will come into a computer that does what? Process that information with the program, which is you're going to learn how to write some of this semester, and then we generate outputs depending on what the sensor is. You need another break? Okay. You need a break?
That would be nice.
Okay, 10 minutes. We had the vice president, and that's what he told us to do. Okay. We're going to deal with luminaries, which is lights, right? Relays. I don't know what a relay is. Solenoids, and then small motors. We do small motors. We are going toward the end, or it's going to hook up a large motor, but the large motor is not going to be part of the control circuit, right? It's going to be hooked up extra. We'll talk about that one. Luminaries, lights. We see lights all over the place. Lights just tell us things. Not only in industry do we use it for light places, we also use them for indicators. When things are right, when things are wrong, when things are running, when things you should stay out of here and stuff like that. Solenoid. So y'all know what an electromagnet is.
Yes.
So anytime we put current through a conductor, it creates a magnetic field. And then if we can use that current to concentrate the magnetic field with metals, so we wind a bunch of wire together, we're wired in the same direction, right? You understand that? And then what we do is we put a plunger in it. Let's see if I got my soul. That was almost fun. So what do we use solenoids for?
Still,
Pulling current, locking, binding, right?
Huh? We could use it for locks. But what a solenoid does, it's what we call an actuator. An actuator is a device that takes energy and converts it into motion. So what a solenoid does is it takes electrical energy and converts it over to a linear motion. And of course, electromagnets, this is my electromagnet. This is not a real good magnet because it uses regular wire. But, let's see if this thing's plugged in. So this is an electromagnet. So what advantage does an electromagnet have over a permanent magnet?
Turn it on and on, turn it off.
And we can also control the strength. So the more current I put through the wires, the stronger the magnetic field is. The less current I put through the wires, the less strong it is, right? And then plus we can turn it off and we can turn it on. So y'all see electromagnets all over the place, right? A solenoid, we use that same feature. I didn't put my camera up, guys, so y'all can see this. This is nothing but a straw. But instead of using a regular wire, I'm using what they call magnetic wire. Magnetic wire is wire that has a really, really thin insulation. And why we do that is you really want to get really good coupling between the wires so those fields combine. And all it is just a straw. Okay. So what I'm going to do now is I'm going to take this and I'm going to pick it up to this. Try to. And then I'm going to take my nail and I'm going to put it into the straw. And what did it do? Pull the nail into the straw. And that's all a solenoid is. So what I've done is I've taken electricity and I've converted it into a linear motion. And this is what solenoids do. And where do we run into solenoids? Well, if you've ever been buzzed in, well, how do they unlock the door? Well, it's solenoid, right? And do you have a washing machine? How do they turn the hot water off and the cold water on? They got a solenoid, and this plunger blocks the water. So when you come around and you turn on the hot water, it opens up that valve. You got an ice maker in your house, right? How does it turn the water on and off? It uses a solenoid. Except here, this blocks the water. And we put power, opens it up, lets the water come in. So y'all run into solenoids all the time, right? Well, that's a solenoid. Now what would happen if I took this right here and put a contact on this thing? So now the solenoid would make and break the contact. So now instead of me going back and turning stuff on, I could electrically control the light switch. Wouldn't it be nice to electrically control the light switch? In fact, y'all got these. You can buy these things where you can turn your lights on and off with your dang cell phone.
Yep.
Right? right? You understand? Well, what are they doing it? Well, your cell phone is being picked up by Bluetooth, whatever you're using Wi-Fi, and then it's energizing a solenoid. The solenoids are controlling contacts, and the contacts are open and breaking. So now we can control contacts with electricity instead of us using manually control the contacts. We can electrically control. As soon as I turn it over to electricity, I can control electricity, so we can have automation. So what a relay is, it's nothing but a solenoid that controls contacts. That's all it is. So we got relays, and a contact is something that we make and break. So you can see this relay right here. So I come over here, I put current through this coil. We call this a coil because it's just wire that's wound in a coil, so we call it a relay coil. And then I put current on there, it generates a magnetic field, pulls this thing down, and comes up here and moves that, and does what? Opens one set of contacts and closes the other. But now instead of me doing it manually, I'm controlling it electrically. And that's what a relay is. A relay is nothing but an electrically controlled switch. And you can do a lot with relays. You can change the type of voltage. So the coil might be an AC coil, but my contacts are switching. It might be an AC coil, but my contacts are switching a DC circuit, or vice versa. The coil could be a DC coil, but the contacts could be controlling AC. Right? Which is what's happening over there. So that relay inside your box that you hook up there to replace your light switch is using DC, but it's controlling AC. We're doing it with a what? Odds are if you went over there and listened, you would hear a little click, which would be the relay actually picking up. You can actually hear the relay. So we could be using 24 volts on the coil, but we could be controlling 500 volts on the contact. So we can change the type, we can change the voltage level through a relay, but what's nice is we're controlling relays with electricity. As soon as I say electricity, we can turn it over to automation, right? So like there's no way now we can go out in my car, most of your car now, you either have a push button that you press, right? You understand? Or you're pushing a little switch, but you got a starter relay out there that's inside your starter that's taking a very small current to pull in the coil, right? You understand it's controlling a lot of current. And we can do logic with these things. So relays. And we call these contacts. So every relay controls contacts. Solenoid does not control contacts. What it's going to do is it's going to unlock doors, or it's going to turn water on or off, or it's going to do something like that, right? Makes sense? So a relay is a combination of a solenoid and your contact. Oh yeah, you got all kinds of relays. You got a bunch of relays in your car. Usually they're outside under your hood. Yeah, you can't. That little light switch that you hear that little light switch when you turn on your lights. Used to you had a big old switch to turn on your lights, and we had the dimmer. We had a dang thing in the floor, which is a big old switch that you had to hit because they were actually controlling the lights. Now, how do we dim our lights? We got something up here on our little steering column, right? We hit. But what you're doing is that little steering column is bringing in a relay, and the relay is controlling the lights. So out there out there, you go up in your hood. There's a little black box out there. You pop it open. There's a bunch of little black squares in there, and they're all relays. And it allows us now to use little tiny push buttons. It allows computers to control that. So odds are when you turn on your lights, it's not even going to your lights anymore. It's not even going to the relay. It's going to your body control module. Used to we had one computer. Used to we had no computers in our car. Then we went to one computer. We called it an engine control module. Now we got a body control module, and now we got all kind of modules in there. We got avoidance modules. I think one guy said the computers run like 7 individual computers inside some of the automobiles. So what you're doing is you're telling a computer that you want to turn on your lights. So now when you get out your car, you put your lights on auto, right? You understand? We got cars that auto dim and auto brighten. And then you get out of your car, you turn unlock your door and your lights come on, right? So you find your car. You can hit that emergency stop, that E button on there and find your car when you forgot where you parked, right? Anybody ever did that? The panic button, yeah. I hadn't done that yet.
When you work that town, using a different.
Oh yeah, when you rental a car, yeah.
For months.
So electromechanical linear actuators. We have these. This is basic. This is off a washing machine right there. That's all that is, a washing machine. You hook up your hot water to one, you hook up the cold water to the other one, and these are two solenoids. And all they're doing is what? Controlling the cold and flow of water. You got one of these. If you look in the back of your refrigerator, if you got an ice maker back there, if you got water in the door, there's going to be these things back there. These are solenoids. These are valves that control the flow of water. These are what we call directional control valves. These are solenoid operated. So what they do is we shift a vein. We call it a spool inside a valve to control the flow of fluids. So we can make robots go up or down or stuff like that.
They pretty strong.
Solenoids is not actually doing it, and it all depends on the size of the solenoids. What we're doing inside this thing is we're shifting. So this guy right here is not, all it's doing is blocking water, right? And it comes in from the side. When you get into fluid power, you might get into like our hydraulic systems on the airplanes I worked on in the Navy that ran 3,000 PSI. You're using directional control valves on there. Well, the solenoid is not actually controlling the flow. It's shifting what we call a spool inside it. So it shifts it one way and it causes the flood to flow one way, and it shifts it other and comes back. And then we have what we call pilot assist. So we can use small solenoids to control what we call a pilot assisted valve.
On that washing machine, you have something that goes down in there that restricts the flow.
That's all it is. It's just the solenoid drops down in.
I was thinking, sometimes you need warm, you need a little both.
Well, that's what it's doing. It just opens up both. It opens up both of them, right? I guarantee you on the back of your.
Well, I've never looked at it. Hopefully it won't break.
These are the types of relays we have. We have what we call a control relay. So what we'll find out is most control circuits deal with two different sections. In fact, we'll look at it. We have a control section. And then we'll have a power section. Now this is done a long time ago because the control section, for years it was like 120 volts, but now just about all your controls have dropped down to around 24, 26 volts. So we can have a control section where most of our relays and stuff are at, and we run low voltage there. And what advantage is low voltage of high? What's the advantage? Same. So 24 volts in a control cabinet now, you wouldn't have to wear any special PPE. You'd wear standard PPE that's required by your company. Most people require you to wear safety glasses. A lot of people wear hard hats, long pants, right? Leather shoes. Some people have to wear steel-toed shoes or metal tarsals, but that's basically depending on what you wear. But then we get out in the power section. The power section is where you're going to have high voltage at, and we're going to put this in a cabinet over here by itself. So you can work inside the control cabinet with all this PPE. You know what PPE is, right?
Yeah. Personal protection.
Yeah, personal protection equipment. Over here, working on the controls for your PLCs and everything, this will be low voltage, so you can work in there without putting on your glasses. Then when you get over there to figure out why this big old 500 horsepower motor's not working, that's going to be where? It's going to be over in the power section. It's going to be controlled by the control section, but it's going to be in another cabinet, right? I'm saying. You go up there and open up that thing, that's where you're going to have to start putting on special PPE to get into there. But it allows us to not have the high voltage inside the same cabinet as the control. This is where our PLCs will actually be. So control relays, the contacts controlled by a control relay never leave the control cable. So they're all inside the control center. This is where we'll learn about doing logic. So when we do logic with relays, relay logic, we're going to do it with control relays. And this is what a PLC is primarily replaced, is these control relays. PLCs, we program them. We don't wire them, we program them. So the big thing about using control, hardwired circuits like that, is if you're going to change something, you had to do what? No, you didn't change the program. You had to rewire it. So used to, when cars started trying to move into automation, they did it with relay logic. And really, they had two lines. They had one they was running this year, and they had the other one they was rewiring for what? For next year. Now we don't do that. Mercedes down there, I think it's down 3 weeks when they ship models. And that's just to verify what they run like 300 cars and they scrap them off. And why? Because they put it together with automation and they tear it apart to see if it's put together. And then after that, they're usually up and running, ready to go. Then we have contactors. Contactors, these guys right here, these are going to be out here in your power circuit. They'll be controlled by your control circuit, but we'll just run wires. But remember, the coil on your contactor can still be rated at what? 26 volts, right? You understand that? But when them contacts close, they might be controlling 600 volts. They'll be where? They'll be in your power circuit. Contactors, these guys are usually used for high power devices. Now the problem we have with motors is rule of thumb, and you could look this up. If you look at the nameplate on a motor, on a new motor, it's got a letter on there, and you look that up, and it tells you what we call the start current, how much a motor requires when it starts. And y'all understand this. Anything that's in rest wants to do what? Stay at rest, right? So your car is sitting at a red light, and you want it to go. What do you do with your gas pedal? Push it down pretty far, right? And then the car starts coming up to speed. What do you automatically do? You raise it up. So rule of thumb, if you don't know the start current of a motor. So when a motor's sitting out there still and you start it, it pulls an inrush. It pulls a lot of current. Rule of thumb is 6 to 8 times.
That's why they said stop flipping on off the light.
Good. 6 to 8 times. 6 to 8 times. So if it took 5 amps to run it at its rated horsepower, then it could take 30 to 40 amps just to get that sucker started. So when I protect this thing, when I protect my circuit with an overcurrent protection device, it's going to have to let those motors start. So those things are going to be rated at least whatever its start current plus probably about 125% over the start current. So it means if the motor doesn't start or if the motor stalls, those overcurrent protection devices are not going to do anything. They'll just sit there and let the motor do what? Just flat burn up. So what they did is they came up with what we call overloads. These are devices that allow overcurrent over time. But once it tries to pull current over an extended time, it automatically kicks them out. And these are called overloads. So we have another relay that's designed to run in the motor circuit, and it's called a magnetic motor starter, and it has overloads in it. So your motor actually hooks in. All the current that goes through to the motor comes through the overload. And that way, if the motor don't start, it don't kick your overcurrent device, but it'll kick it out with the overload. Does that make sense? Or if the motor ever stalls, it'll kick it out without burning up the motor. So that's our 3 categories of relays. Control relays, these are low current devices. These guys can have all kind of contacts on it. We got one up here. This only shows one contact. This is one of our control relays here. Let me see if I can find it. So here it is right here. This guy's got 1, 2, 3, 4. This one's gone. It's just 5, 6, 7, 8 contacts. And most of these relays have what we call a manual override. So the solenoid is right here. And then it's going to move some type of armature or plunger. that causes this guy right here to move. And it's going to cause either contacts to open or contacts to close. So we have what we call normally closed contacts. These are contacts that are closed when the relay is not energized. And then we have normally open contacts, which only close when the relay is energized. Right? So when you energize it, your normally open contacts are going to open, and your normally closed contacts are going to open, and your normally open contacts are going to close. Most of these relays have what we call a manual override on them. You have to be real careful about using these guys. So what you just did is you've taken away every safety procedure that's built into your automated system. We had a guy at US Steel got killed when I was out there. By a guy went in and overrode the wrong relay. They locked out everything, tagged out everything. He was up the top of number 8 blast furnace. Number 8 blast furnace was a pressurized furnace. And what they did is they had a conveyor belt that came up one side and they dumped material into the top. They would open a gate and let it fall in, then it closed it. And then they'd open the bottom of it up and let it fall in. They were working on one of the gates up there. They disconnected, everything disconnected, and the guy went down there and closed it. And he was looking for the other gate, and the other gate came up and cut the guy off. I do it wrong. Forcing the wrong way. We call it forcing. We'll look at forcing on PLCs too. PLCs we have to go to force contact. But you need to be real careful and understand the consequences of forcing, because you've taken away every safety feature that's built into that system. Right? All the sensors that sense if somebody's slid up there. So this is the control relay. Like I said, this is where we would hook up the coil. Then when we energize this, it would cause the solenoid to move, right? And it would cause this to move and you connect it to the contact. So this control relay has eight such contacts. You can look, one set is missing. And a lot of the relays we use in the industry is actually what we call double break contact. So we'll come up here and one contact would look like this. If I draw them vertical like this. And then we'd have something down here that they would be made up in. This would be a normally closed contact. And then we would wire it here. So this is conductors. So when this thing closes, we create a path. Well, what it does is there's a spring in there, and this thing kind of floats. So what happens if the thing breaks and one of the contacts trying to freeze, then it would automatically tilt up and break the other contact loose. So a lot of the relays that you see in industry use what we call double break contact. And a lot of the push buttons we do too. So you can kind of see how those contacts float in there. Symbols of the trade. So this is some of the symbols we need to know. Y'all understand, y'all took blueprint reading, right? Y'all do that. What's the purpose of symbols? What do symbols allow us to do? Yeah, simplifies. It makes the circuit more understandable, right? You understand. It's like when you go out and buy a TV, you get what we call a pictorial drawing, because they're giving these to people that don't understand that. So it shows you what a VCR looks like, and it shows you how, y'all ever did that, bought it on TV, you get that pictorial, but look how big that thing is. What we do is to simplify things and make it easier to understand. We represent different mechanical devices with symbols. And these are some of the symbols that we're going to use. So what's that round one up there? Can y'all read that? No, right up there. That's a circuit breaker.
Oh,
that's a relay coil. That represents the coil of a relay. Just a circle. Are we okay? That makes sense? What's the next one to it? That's an income. Yeah, y'all should have had these same symbols, right? If some of y'all hadn't had it. What's this guy right here?
A no contact.
No contact. Normally open contact, right?
That was normally closed.
And this is a symbol for normally closed. We're going to use a lot of these up at the top. What's the symbol for?
The push button.
Yeah, these are usually the symbol we use for momentary contact push buttons, which means that they're only true or false when you hold them down, right? So we run into a lot of these. I bet y'all seen a lot of these.
Some of them got the double push.
And then a normally closed. And these are other symbols. These would be for a flow switch. Float switch. What the flow switch does, it sits when something is, when the fluid is flowing, right? Understand that? And a float switch would give us a liquid level when liquids are at a certain altitude. Pressure switches. These are all what we call digital sensors. These are digital. Some people call them binary switches or sensors. Digital sensors are either going to be true or false. They're not going to be anything in between. Everybody understand that? So we went into a lot. This is probably the predominant sensor that we use in automation. It's either there or not there. It's either at this pressure or not at this pressure. It's either at this temperature or not at this temperature, right? And then we have analog sensors also. This is where relay logic had problems with is analog. Relay logic worked great with digital stuff because it either energized a relay or not energized a relay, right? So relays are digital. And contacts are digital. They're either what? They're either open or closed. So relay, we had big relay logic. We couldn't do temperature. We couldn't sense speed. We couldn't do any of that with relay logic. We used to have these big complicated computers that ran this. So when they put number 8 blast furnace out there, the number 4 galvanized line was nothing but relays. You'd have been amazed. I mean, these whole houses, they were air conditioned relay houses. They had 3 of them, three different sections of the line. They had 3 of these relay houses, and they were just stuffed full of stuff. Nothing analog though, just everything was what? It's digital. These are true or false. They came out and put number 8 blast furnace out there, and that was computerized, but it had these big old computers that was running that. They came in before, this was after I left, and they replaced most of the relays inside the relay houses at the 4 galvanized line with one PLC. So instead of having a room that big, they had plenty of room to go in there and sleep because it was there. Yeah, we'd go in there and find pillows and stuff in there all the time. So these are our symbols, guys. So I'll run this off and give it to you. Now, the only symbols that we use inside the PLC program is we're going to have special symbols we'll look at, but when we get into relays, we're going to use normally open, normally closed contacts, and then the relay coil. But when you wire up a PLC, so when we wire up a PLC is not designed to run heavy load. But a PLC can bring in a relay, and the relay can do what? On every load. A push button. So when we wire the PLC, we have to use the symbols that the electrical symbols for push buttons and stuff like that when we wire the PLC. We'll look at that a little bit. This class, we don't actually wire a PLC, but we don't physically wire the PLC, but we play like we wire it, but we draw it. We draw how we use it. If you take the PLC 3 class, you'll actually wire the PLC. Any questions on this? Well, like I said, I'll run this off and get this thing. I need to make myself a note. So, this is a relay logic circuit. This uses relay. Now, we call this a ladder diagram. Can you see how I got that name? It looks like a ladder. And what we do is on the outside, L1 and L2, this is a generic term that we use for the power rails. So these are going to be the power. So what we do is we hook circuits between L1 and L2. Each circuit, we call that a run. Does that make sense? So we called it ladder. We called it a ladder diagram. And we call the individual circuits a run. Make sense? So here, this is a symbol for a relay. I know this is a relay contact. I know it's a relay coil. Huh? No, this is not a motor. This is a relay coil. This is not a motor. A motor has a different symbol. This round circle in motor controls is a relay coil. It's got a name they call it. It's got a name. They named it IM.
Oh.
Okay. In PLCs, in RS Logic 500, they call them symbols. So what we're going to do is we're going to give these devices names. We're going to have to assign them to something, but we're going to give them names. And it's nicer to deal with names than to deal. It's just like a phone number. So how many people know all the phone numbers that's in your contact book? Right. I had somebody call and wanted to know my son's name. And I didn't have my cell phone with me. And I said, I don't know. Well, I don't even know my son's number. Right? I know my wife's number. Huh? But what we do is we access things by name. Alan, they've moved away from symbols. Now they call them tags. So all our PLC programming languages now are what they call tag based. And what you do is you give a device a name. So that M is not, it's a name. Right? Does that make sense? And what it does is it tells us what contacts are controlled. So I look here, I see this guy is called, this is given the name of M. And down here I've got a normally closed contact that has the name what? M. That means as long as M is not energized, or if we don't put current through it, this contact right here would be closed and this light would be off. Okay. I've got another contact up here called M. It's got the same name as this coil. So what that means is this contact is being controlled by this coil. So right now the way it sets, this contact would be open, this contact would be closed, and this light would be on. Now these are overloads, so that means this is a relay that controls the motor. So what we would do is somewhere we have a power circuit. In the power circuit, we use a symbol. This has 3 overloads, so it's controlling a 3-phase motor. This is the symbol of a 3-phase motor. And what I would do is I would come over here and I would have an M contact right here. And then I would have an M contact right there. And then I would have an M contact right here. And then we have the overload sensors. I forgot to draw that in there. This is a symbol for the sensors that sense the overload. And up here, what could this be? Well, this could be 660 volts, 3-phase. But it's not inside my cabinet with this. This is inside the wall. Right? You understand? Does that make sense? So I come over here and I press this button right here. I don't hold it. It's a momentary contact push button. I come up here and press that button. That's going to allow current to flow over here. It's going to go through the relay. It's going to close that contact right there, and it's going to open that contact right there. Then I let go of the button. What's going to happen when I let go of the button? No, it's going to come now, but look at this. I close this contact right here. So what happens now is now it has a secondary path where it comes up here, and M is going to stay energized. So all I did was up there is I hit a little button over here, green button that says start. I hit the button, I let it go, and the motor turns on. And it stays on because we seal it in, right? You understand? This is called a seal-in circuit. It's called a memory circuit. This is a very popular circuit because it allows me to use a push button to control a relay instead of using a switch. Huh?
Like a car.
Yeah. So yeah, you come over and push your car once, right? Of course, now your starter knows when your car starts. I just realized my car does that. My wife's, something happened to the fuel pump, and she pressed the start, she hit the ignition key, and when she let it go, it just kept trying to start. It just trying to start. A lot of cars do that now. My HHR does the same thing. So I don't have to hold the key. All I have to do is just hit it, and it'll turn over until it cranks. And now we have these push buttons. Now cars have push buttons. They won't even crank unless you're. So a lot of cars now you don't even have your key is not a key, it's a fob, right? You just carry it around in your pocket. And if you get away from your car, what does it do? It turns it off. Of course, there was a story about some people that died because of carbon dioxide because where they were at in the house was not far away from the car to do what? Turn it off. So how do I stop this thing? How do I break it? Yeah, I got a Norman close push button right here. As soon as I come over and press that, it breaks the circuit, the M drops out, the motor turns off, and this light turns on saying the motor's turned off. We call this the sealing circuit, one of the, probably the most used circuits in manufacturing. I got two buttons up there. I got a start button. All you have to do is do what? Hit it once, let it go, motor starts up, and you get ready to do what? Of course, a lot of times now we put the screen on the HMI panel. What does HMI stand for? Yeah, human machine interface. So there's a lot of things that could fall in that category, but we call these touchscreen panels. They call it, a lot of people call them HMI panels. Except Rockwell calls theirs panel view. Siemens calls them HMIs. Let's see why it's called ladder. Because it looks like a ladder. This is nothing but a single element series circuit. These I have hooked in parallel. But this does not mean it's a parallel circuit because these are control devices. Control devices does not control, decide whether it's a parallel circuit. So this is a single load, and this is all we have. We either have single load series circuits or we have parallel circuits. Everybody okay? And this is the language that our PLC is going to program. It's going to program in ladder logic. And why did they choose that as the primary language? Because we did relay logic for years. So the first automated systems, guys, was done with nothing but relays. We call it relay logic. And that's why we had 500-600 relays in that one house trying to do all that logic. Not trying to control the motors. We might have had one relay that controlled the motors. All those other relays was in there just to do the logic, just to do the automation part. And that's what PLCs will replace. It replaces all those relays that were in there that did nothing but do what? To automate the system. So we can program this thing and then wire our motor starter outside of the actual PLC effect. So this is the symbol for the overload right here. So if one of the overloads trip, it's going to open up, drop out, and the motor will drop out. So this is a typical relay logic symbol. So this is a parallel. So this is a rung. But it's parallel, right? Understand that. So here's a circuit that runs from L1 to L2. This is a rung. So we do have a lot of parallel circuits. We don't have any two devices. So it's going to be a one load series circuit. It's going to be a multi-load parallel circuit. So here's all our control devices over here on the left-hand side. So this is true even for PLC. So our control devices are going to be between L1 and the load. How many control devices can we have? We have tons of them. I mean, a lot of them. You know how much control we need over them. And then our loads are going to be between the control devices and L2. The only thing that's allowed between the control device and L2 are these overlays or motor starts. Notice everything. So I know this right here is a motor start. There's a light bulb. That's a symbol for a. What's this a symbol for? No, it's only got two. If it was a resistor, it would have to have at least a few. Oh, good, yeah. So that symbol's not on here, guys. I need to make sure I put that on there. It is. That's exactly right. I don't have that on the chart. I need to put that on. But that's what's saying. So what's the difference between a solenoid and a relay? Well, a relay is a solenoid that controls contact. A solenoid is just a device that takes an electrical thing and generates a motion, right? Straight line motion. So what does that solenoid do? It might be turning on the gas to something. It might be opening up a valve. It might be doing all kinds of things. But it's not controlling contact. Okay. So we can't put a motor starter inside a PLC because this is a power device. The PLCs are not power devices, they're control devices. Right? But we could put a regular control relay inside the ladder diagram for the PLC, and then you did control the motor. You understand what I just said? So, here's the power rails. Control, I don't know what it is. Everybody okay on L1? So what we call those power rails, L1 is usually considered to be the hot leg. That's not a real good term, but that's a term an electrician uses. And L2 is considered to be the circuit common. L1 or L2 can either be, so these could be either DC or it could be PLCs is moving more toward DC. Then we call these what? So what is a rung? A rung is an electrical circuit that runs between L1 and L2. Now L1 and L2 are generic terms because they get very confusing. If you look over here on our disconnect over here, you see L1, L2, L3. That's 208. All my relays are designed to run on 120 volts. Well, I don't take that L1 over there and hook it up to the relay. The relay will burn up just like that. So what are we running through? It's that big black thing up there. Top right beside the disconnect. Starts with a T. Transformer. So it's taking the 120 volt or 208 and stepping it down to 117, 112 volts for the relay. But on the other side, it's called L1 and L2 too. So when you get into real diagrams, they might call this, like PL1 and PL2, or they might give it another name. Usually they put L1 in there somewhere, but they'll give it another name besides L1 and L2 because that's what we call the three-phase lines. Three-phase line over here, we call this L1, and we call this L2, and we call this L3. And this happens in motor control. This might be DC, and this might be 24 volts AC. Somebody don't know that. They take this L1 and hook it up right there. What do they do? You burn up your whole system, right? You understand? So normally in the controls they give it a little different name besides L1 and L2. But L1 and L2 is usually in the diagram. I call it PL1 and PL2 because that's what US Steel called it in their diagram. It's extremely important to learn the symbols of the trade. Y'all that's had blueprint reading, you can understand that. Well, you understand symbols. Symbols allows us to draw things a lot smaller, right? Understand that? Instead of drawing pictures. Can you imagine if me trying to draw all that stuff out there, trying to draw the actual pictures of that instead of representing symbols? That's not a complicated diagram. So we have symbols. We have symbols that represent sensors, and we'll look at some of the symbols too. And we'll look and see how to connect the PLC. But like I said, in this class we just don't have. Everybody okay on volts, ohms, and resistance? 6.25. So I got that wrong. I said 6.28. What's 6.25? Yeah, it's 1 coulomb. So basically, an amp is 1 coulomb in motion. So a coulomb is 6.25 times 10 to the 18th stored. So capacitors and stuff like that, that's one of their ratings to figure out the capacity phase, how many coulombs they can store. But as soon as it starts moving, it becomes amps. Of course, we know this, right? The Ohm's law. You okay with Ohm's law? D or E is equal to I times ohm. Now I put ohms over here because ohms is opposition. Back in DC, you learned that the only opposition you use was R. But in AC, we have something called X of L and X of C. So these are oppositions. But still, they're oppositions in ohms. But the problem with X of L and X of C, it varies with how fast the AC changes, which is really cool. So on a capacitor, which is X of C, the opposition goes down as the rate of change goes up. So at 1,000 hertz, this thing might have 100 ohms worth of resistance. At 10,000 ohms, it might have 5 ohms of resistance. So these guys are not like resistors. Resistors have the same opposition no matter what the frequency is. Capacitors and inductors vary their opposition with frequency, which is really cool. So it allows us to set up circuits that are frequency related, or frequency sensitive. Like I said, the radio in your car. I used to, on your OTVs, you could snap off the back and you could actually see inductors on the channel switch. And that's what you was doing. You was setting up a tune circuits to allow what we call the carrier to come through. So what they do when we're sending information, we call it multiplexing. Anybody heard of that term, multiplexing? Multiplexing is when we let multiple signals share the same media. Media is what information flows through. So when we let multiple, so right now I'm literally sitting in a multiplex media. So air is a media. And how many signals do we have flowing through this air right now? Is your cell phone hooked up to wire? So how is your information coming to your cell phone? Through the air. Through the air. Not from that antenna. That antenna, you're not connected to that antenna. It's coming through a media, and the media is air. All your commercial TV stations are air. All radio transmissions are air. All satellites are air. That's the media they're using. So how many signals do we have riding on that air at the same time? A lot. We call that multiplex. Well, what's that? Well, if magnetic waves could move through something, it would move, right? You understand? So magnetic waves will move through water. How much? We don't know air and water. Fish knows air and water. So magnetic waves, like submarines, use a lot of water for their medium. So they send radio signals through waves, but they're real low frequency. We call them ELF. I don't know if you've ever heard of that. Because high frequencies don't like to move through water and solid. So they use a lot of ELF. But I don't know if y'all ever seen movies where they trail those antennas out of the back of that submarine like 2 miles long so they can transmit their low frequency. So high frequency, the higher the frequency, the smaller the antenna. So what we do is we take the information and we put it on a frequency we call a carrier. So somehow that carrier changes that frequency. And two of them you're familiar with. We have AM and FM. And what we do is AM the signal changes the amplitude of the carrier. On FM, the signal changes the frequency. And that's the technique of doing that, taking information and placing it on a carrier, we call that modulation. Then we have a device that takes that, so we can modulate it. We can put hundreds of signals on your cable TV. On that cable, we can put hundreds of signals on it. But eventually, we're going to have to be able to select which channel we want to let come into our TV. And so we have to have some type of demodulator. So how many of you have a modem in your house? What does that stand for? It's a modulator demodulator. So what it does, it modulates your signal and places it on that cable. It does it at a certain frequency that doesn't interfere with any of your cable TV channels. They all have their frequency. You send it somewhere and then eventually they're going to have to do what? They're going to have to demodulate. Well, this is where your inductors and your capacitors come into play. So what we can do is we can set up what we call tuned circuits, which allows a carrier to come through and blocks all the other carriers. So you can look on your radio when you tune 93.7, it says 93.7 megahertz, right? You understand? And what's that? Well, that's the carrier frequency. So what does it do to all the other channels? It blocks them. So your radio is a demodulator. It's not a modulator. You don't put information out, but it definitely brings information in. So it allows us to set up tuned circuits to allow certain frequencies to come through and do what? Block other frequencies. And that's what these guys do. They vary their resistance to frequency, their opposition. It's not And they cancel each other out. It's really cool. And they also do phase shift. So I'll see if I can find my unit and actually show you a phase shift. It's really, really neat inside an AC circuit. So these guys right here have functions in life. We can set up 2 circuits with them. We can filter stuff out so we can get rid of electrical noise that we don't like. So like popping in your radio. I don't know if y'all remember old days. If you had a real old car, you hear your radio was going tick, 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 tick. What was it doing? Picking up the spark plug, right? But now we don't have that problem. Plus FM, that's a lot too. And that's why AM hums. Everybody listen to AM anymore? Lawson's got a radio station that that radio program they put out, and it's on an AM channel. But if you ever listen to AM, if you just flip your radio over on AM, it hums at y'all. Because it's very noisy, and FM helped out with that. So y'all worked all these problems, we're not going to do it anymore. Everybody okay on voltage drop? Ideal circuits, all the push provided by the voltage source is distributed across the circuit loads. Current flow through opposition of the loads produces work. That circuit was designed to deliver. Everybody understand that? So if I push current through resistance, it's going to drop a voltage. So we assume wires have 0 resistance. Is that true? What determines the resistance of a wire? The material, right? The size, the length, and the temperature. So the closer, the smaller the wire is, the smaller we can make them. But the further they go out, if they're going to handle that same power, it's going to be dealing. So most of your conductors are rated in ohms per kilometer, ohms per mile. In a real circuit, all devices come have opposition, either resistance or reactance. Even conductors have opposition. And this is what we just got through, right? Temperature, material, size, and all. And reactance, we're not going to talk, it's determined by the frequency, but we're not doing it. So available load is decreased. This is called a wall. Voltage drop. Everybody understand that? V or E is the lifetime zone. So here's an ideal circuit we use a lot. This would actually be a true circuit. So those wires have what? Resistance. But if you use the right gauge, right? You understand that? We use the right material, we use the right gauge. Normally we assume it to be 0. But Alabama Power can't assume that because they're not running their wires this long, they're running them long. That's why every once in a while, even on your cell phone, you'll see a big box up there on your cable, and all it is an amplifier because the cops they happen to do what? Preamplify. Most of your substations automatically change the ratio of the transformers to try to maintain a constant output. The big substations, those things are very complicated. So this is an American wire gauge. This shows you the wire number. And there's a formula, by the way, to figure out which number goes with which gauge. Basically, what you need to remember, the higher the gauge number, the smaller the wire. There's a formula. And after a while, you'll learn it. So it says that we deal with a lot of 14 gauge wire in our house, copper. This is all copper. And it says this is millimeters. It says it has 2.525 ohms at 1,000 feet. Now normally this is at 20 degrees centigrade, which would be around 60 something degrees. So normally when you look at a ampacity chart, it gives you a temperature that's that. So notice the resistance is rated in what? Ohms per 1,000 feet. Now as the gauge number goes up, the size goes down. So 20 gauge wire, we use a lot of 22 gauge wires in here, so it's going to have over, but we're only using wires that are what, 6 inches long. So if you said, okay, if it's got 30 ohms per 1,000 feet, then how much would it have for 1 inch, right? It'd be down in the milliohms, which we can ignore, right? In fact, Most ohm meters won't even measure it. So the American wire gauge actually goes up to 24 gauge. No, it don't. It goes up to 40 something gauge. On the small side, the biggest it goes up to, we call that a 4-aught. Every time I say that, I remember Beverly Hillbillies, Death Row, that's what he used for zero, it's called an aught. So we call that 4-aught. This has a diameter of what? Of almost a half an inch. And it's only got about 49 milliohms per thousand. And anything above that, they rate in what they call circular mills. They call them KC mills, thousands of circular mills. So these are going to be big wires. Anything above 4-aught, which is about half an inch, right? After that, they do what they call KC mills. And what's nice about KC mills, the bigger the KC mills, the bigger the wire. On the American wire gauge, the bigger the wire number, the smaller the wire. And like I said, over time, if you're an electrician, you definitely know what 14 gauge wire is. What's the other standard used wire? Do a lot of 12 gauge wire in residential wire. Do a lot of 8, 10 and 8. That's run HVAC systems. There's not any more than that, and you're running to the house. Commercial wiring will run to a lot of different. Here's an ampacity in free air at 25 degrees centigrade. And you can see a 14 gauge wire is rated at what? 32. That's if it had no insulation on it, and it was at 20 degrees centigrade. Roughly about 65 degrees centigrade. So when the National Electrical Code came out and they said you use 14 gauge wires, are they going to rate it at 32? No, because they're all going to be insulated. They're all going to be ran in walls. They're all going to be ran all the way from the equator all the way up to Alaska. So one thing they wanted to do is they wanted to rate it at an ampacity where you could run it through the ceiling of your house in Alabama during the summertime and still say it was rated, it could handle this much current. Anybody know what NEC rates a 14 gauge wire? Okay, so what is a National Electrical Code rate a 14 gauge wire? What do they rate a 12 gauge? Here's the NEC chart. They rate a 14 gauge wire. 14 gauge, they rate it what? 50 gauge. So they dirate it so much. Why do they dirate it so much? Why don't they rate it at 34? Because it's not going to be, first of all, it's going to be insulated. Right? You understand? Second, it's going to be run in Alabama, right? In the summertime. That makes sense? And notice they change the rating depending on the insulation that we run. So these are different common insulations that we run in, not in house wiring. We run them in. When they move toward commercial, they move a lot into single wires. In residential, most of ours are cables, right? You understand? So notice we run this insulation right here at 90 degrees centigrade. Am I that funny? 90 degrees centigrade, and they rate it at what? 25.
What does that number mean now?
25 amps is what it's rated at. If you use this, if you use this type of insulation, so if you use this type of insulation, which is rated at 90 degrees centigrade, which is 194 degrees Fahrenheit.
Most of the cable I ever bought was
Romex.
14.2 or 10.3.
Or 14.3, or 14.2 with a ground.
Yeah, that's right.
So 12 gauge is rated at 20 amps and 14 gauge is rated at 15. And as long as you maintain that.
So this is like an average would be for United States or?
No, National Electrical, it's our code, it's for the United States. So Europe and all of them have their own codes, have their own electrical code.
You were talking about the equator.
Well, I was wrong with it. anywhere in the United States, this guy should do it. So we didn't get over to Bill and A. We'll come over and you see what we're going to have to go through next class. Here's AC.
So are you teaching AC? Because I see it, that's what it says on. Are you teaching AC?
No, right now it should say staff. On Blackboard it might say me, because I had to copy the Blackboard something. So if you look on Blackboard, it says I'm the instructor, but if you looked at the welding class, I would be down as an instructor too. So since I'm a department head, I'm put down as an instructor for all our Blackboard classes.
So do you know who will be teaching that class?
It's either going to be Miss Allison, probably not. It's probably going to be Mr. Foster. He's an adjunct instructor. He's not full time, but he does AC for us. So does a really good job.
Y'all teach them about classes.
We cancel quite a few. Oh, wait a second, guys. You know what I forgot? I forgot to take roll. Y'all sign y'all's name back here.
Now, this book is the one we get.
Everybody got the books? Y'all, anybody's got the book, hold it up so the people that hadn't seen it can see it. And also the lab book.